All right, here we go with the first part of 2.4, getting into the chain rule. This is a super important concept for derivatives. After this, it really becomes embedded in everything that you do with derivatives. So really, really important lesson on this one. It is a little bit lengthier than some of the other videos, but it's kind of necessary. So I'm going to have Mr. Martin go through the first part with you. I'm going to take over for the last two examples on examples 8 and 9. So here we go. Follow along.
It tells us how to handle taking the derivative of a composite function, something that looks like y equals f of g of x when you take one function and plug it into another function. How do we differentiate that? So the chain rule says if y equals f of u is a differential function of u, and u equals g of x is a differentiable function of x, then y equals f of g of x is a differentiable function of x. And the way we differentiate this then is we say dy dx equals dy du times du dx. So in other words, if I'm taking the derivative of this function, it would be dy du. That's this one. If I take the derivative of this function, that would be du dx. And you multiply them together. Generally, we don't see this form nearly as often. I know it does kind of look like this might follow rules where you can cancel out the du here and the du here and get dy over dx, and that's why it's this. It really doesn't have much to do with that. It's just a notation situation. We're going to focus on. Okay? It says the derivative of f of g of x is f prime at g of x times g prime of x. In other words, let's talk about the outside function and the inside function and the inside derivative here. Okay? If we have the outside function would be f of something. Okay? In this case, the inside function is g of x. The outside derivative would be f prime at whatever, and the inside derivative would be g prime of x. So what this tells us is if we have the composite function f of g of x, the derivative is we take the derivative of the outside function, okay, at the inside function, meaning leave the inside function the exact same. Notice the inside function here was g of x, this is what the inside function here is g of x, and then times the derivative of the inside function. This part right here times the inside derivative is the most powerful part that is the most common mistake people make, and a lot of times forget to do that. So let's take a look at some examples. I know it probably sounds complicated right now, but the examples will help clear it up. So here we go. Example 1. Find dy dx for y equals the 7th power of x cubed minus 5. So the outside function, the way we want to think of this is if I'm identifying, for every time we do the chain rule, we want to identify the outside function and the inside function. The outside function is basically just something raised to the 7th power. Forget about what's inside here. How do you take the derivative of anything to the 7th power? Well, you move the 7 in front and you raise it to the 6th power. Okay? The inside function then would be whatever's inside there. In this case, it is x cubed minus 5. What's the derivative of this? You got it. It is 3x squared. So dy dx is going to be written as, first we're going to differentiate, according to this rule here, we're going to differentiate the outside function, leave the inside part the exact same, and then multiply the inside derivative. So we're going to differentiate the outside function, which is take the 7, put it here in front, leave all this the exact same, raised to the 6th power. So the first part of it looks like this, the 7 comes in front, leave all that part the exact same, that's the g of x that stays the same right here, and then raise to the 6th power. Okay, so that part right there is this part here. That's the take the derivative of the outside function and add the inside function. So we're going to take the 7, move it in front, leave all this the same, raise it to the 6th, and then this part here tells us we need to multiply by the derivative of the inside function. We'll call it the inside derivative. So now what we need to multiply by the inside derivative, the derivative of this part here is 3x squared, and now when you clean it up, you get whatever you get. What we've just seen in example 1 is an example of what we will call the general power rule, because as you can see here, guys, this chain rule will apply to any composite function. It works here pretty cleanly because we have something raised to a power, and it looks like we can use the power rule on that, but the chain rule will work for things that aren't raised to a power, like the sine 5x or something like that. Okay, so This example 1 here is an example of what we will call the general power rule. If I have y equals u of x, some function of x raised to the nth, where u is a differentiable function of x, so this is some function inside here, and n is a rational number, okay, it's a rational real number, then the derivative of this function here is the same thing we did up in example 1. We'll take n, put it in front here, leave this all the same, make this n minus 1, and then times the inside derivative. So that's what this looks like here. Okay, n times, leave this all the same inside, n minus 1, that's the power rule we did here, that's the 7, leave all this the same, and the 6, and then times the inside derivative, the derivative of whatever was inside there. This part here is that part right there. Another way to write this then, maybe a little more cleanly, is this. If we have the derivative of u to the nth, where u is some function of x, so don't think of u as just the letter u. U in this case is a function of x, so it might be the sine of x, or 5x cubed minus 7x plus cosine of x, something like that. Any function of x right here. So the derivative of that to the nth is n times u to the n minus 1 times u prime, where u prime would be the inside derivative. Okay? Example 2. First of all, we want to rewrite this one. How can we rewrite this as a power? You're used to that by now, hopefully. That's going to be 4x plus 2 raised to the 2/3. Now let's do the power rule on that we just did. Go ahead and hit pause and do it on your own. So now that you've tried it,
What does this look like? Well, when you bring the
2/3 in front, you get that times the original expression, leave that the same inside, and subtract 1 from the exponent, you get negative 1/3, and then you're not done. The most common mistake is to finish right there, okay, to forget to multiply by the inside derivative. What's the inside derivative of this? 4, so you need that, and then you clean it up, and then put it in whatever form you got it. So that's the final answer for example 2. Example 3, all of these I would expect to see on quizzes and tests. This one's pretty common. First of all, this says find g prime of x if g of x equals 6x plus 5 to the 3rd times 2x minus 1 to the 4th. Well, obviously, we don't want to expand this out, and then multiply and get some ridiculously long polynomial. Instead, we need to use the product rule. So think of this, including the raised to the 3rd power, as the first function. This here to the 4th is the second function. So let's set up the product rule. So we're going to do first times the derivative of the second. So the first, we'll keep it the exact same as it was, 6x plus 5 raised to the 3rd. Now we need times the derivative of the second. So what's the derivative of this thing using the chain rule that we just learned? The 4 comes in front. The 2x minus 1 stays there exactly the same. And that gets raised to the what? To the 3rd power now, and then times the inside derivative of this, which is 2. So this whole thing here, from the 4 to the 2, is the derivative of this part right here. So that's first times the derivative of the second, plus, and now we need second times the derivative of the first. So the second is this, and now the derivative of the first, we need the derivative of this whole thing here. So that's the 3 comes in front, leave the inside part the same, raised to the next lowest power, in this case 2, and then times the inside derivative, which is 6. So we can't leave it like this. We are told we need to simplify and factor. So now, let's see what real numbers we have. Let's do there's really 3 parts to each of these terms right here. There's a real number here is 8, and the real number here is 18. So what's the common factor for both of those? We have 8 and 18. We can pull out a 2. So we got a 2 there. And now, the trick here is to factor out the least power. We will say that off and on through the remainder of the course. It's a technique you learned last year. But now look at, see how there's a 6x plus 5 in this term and a 6x plus 5 in this term? What's the least power for that expression? Well, this is the second, and that's to the 3rd. So we need to factor out for that and for the 2x minus 1. What's the least power there? It's to the 3rd. So we will pull out a 6x plus 5 raised to the least power, which is 2. And now we're going to pull out the 2x minus 1 raised to the least power here, which is 3. And now we're going to write a bracket here and ask ourselves, inside this bracket here, we will have 2 expressions that are basically doing this distributive property backward. I need to ask myself, this whole thing times what for this first term? There's going to be this plus here will come right here. This whole thing here times what will give me this whole thing here. So let's do real numbers first. 2 times what gives me 8. Yes, I'm going to have this 4 here first. Okay? Then I need to ask myself, this whole thing times what gives me these two parts here. So remember, we add exponents. If I had an x to the 5th times what would equal x to the 7th? It would be x squared. We add the exponents. So in other words, 6x plus 5 to the 2nd times what equals 6x plus 5 to the 3rd. Well, I need to add the exponents. In other words, 2 plus what equals 3, and that's the first power. So it's raised to the first, which we don't even write, but there's a little 1 right there. In other words, this times this to the 2nd times this to the 1st gives me all of this to the 3rd. Okay? And then we put, do I need the 2x minus 1? No, because this already was the same as this, so we don't need that factor at all. So now we do plus, and now what remains? Now we got to ask ourselves again, for this term, this whole thing times what gives me this whole thing. So now I have to do the real numbers. 2 times what gives me 18. The answer here is 9. So now look at this part here. 6x plus 5 times what gives, or 6x plus 5 to the 2nd times what gives me 6x plus 5 to the 2nd. Well, so I don't need that factor at all because it's the same. So now do the 2x minus 1 to the 3rd times what gives me 2x minus 1 to the 4th. And so again, we need that factor raised to the first power, so that this whole thing to the 3rd times this whole thing to the 1st. You add the exponents, you have 2x minus 1 to the 4th. So now we're not done until we clean it up. We have to combine like terms right here, and now we get whatever we get. So that's our final answer, as ugly as it is. These next 3 examples are actually great examples because they're very similar to each other and helps us kind of examine how we treat the chain rule when we have a composite function of 3 different functions. There's an outer function, a middle function, and an inner function. It gets a little complicated, but we'll go slow and take baby steps through it. So right here, how do I identify the inner function, middle function, and outer function? Well, it's always, if I were to plug in a value for x, like say pi, then, or 1, let's just plug in a simple number, let's plug in 2. If I were to plug in a number here, what would I do to it first? Okay, and then what would I do to it after that? And then what would I do to it after that? So this one here, there's actually only 2 functions in this expression. First, if I were to plug in a 2 here, I would have to cube it and multiply by 5. So this is the inner function. Then I would take the cosine of whatever that is. And so that's the outer function. So that's a pretty simple chain rule problem. Identify the outer function and the inner function, and now apply the chain rule. So we, same as above. We differentiate, let's go back to our general rule here. We differentiate the outer function, leave the inner function the same, and then times the inside derivative. So, if I go back to this problem here, differentiate the outer function. Okay, so that means what's the derivative of the cosine of anything? The negative sign of that thing. So now we leave the inner part the same, so that's going to be 5x cubed. And now times the inside function's derivative, so take the derivative of that, and you get whatever you get. In this case, it is negative 15x times the sine of, negative 15x squared times the sine of 5x cubed. That one was pretty simple. These next 2 have actually 3 functions going on. That's what I was referring to earlier. There's, if I were to take a 2 and plug it in here or here, in example 5, 6, what would we do first? Here we would multiply by 5, so 5x is the inner function. Then we would take that and cube it. So the cubing something cubed is the middle function, and then we would take the cosine of that whole thing, and that's the outer function then, okay? So down here, how is that different? If I were to take a 2 and plug it in here, I would multiply by 5 first, so 5x again is the inner function, and then I would take this and take the cosine of it, because I can actually think of this whole thing as the cosine of 5x, all in parentheses with a cubed on the outside. That's what this notation tells us. So the inner function here is 5x. The middle function is the cosine. Okay, because if I were to plug a 2 in here, I would take the 5x, or 5 times 2 first. Then I would take the cosine of 10, and then I would take that and cube it. So cubing it is the outer function. So let's go back to example 5 and take a look. How do we do this? Well, when you do the chain rule with an outer, middle, and an inner function, just like above, when there was only 2, you do the derivative. You work from the outside function in. So here, this is where it gets a little confusing, but practice will get us where we need to go. We're going to take the derivative of the outer function at the middle function. We'll leave the middle function the same. Then we'll multiply by the derivative of the middle function at the inner function. and then times the inner function's derivative. Okay? So here we go. For what's the derivative of the outermost function here? What is the outermost function? We said it's the cosine of something. In this case, it's 5x squared cubed. So what's the derivative of the cosine of anything? The sine of, negative sine of that thing. So the first thing we have is that. Okay? Notice we're going to take the derivative of the cosine of this whole thing becomes the negative sine of this whole thing. And now we need to multiply by the derivative of the middle function at the inner function. So what was the middle function? The middle function was cubing something, so we're going to take the derivative of this part, which is bring the 3 in front, leave all this the same, and make that a 2, right? So we've got it times 3 times 5x raised to the second power, and then do the inside derivative, which is 5. And so, again, the way we think of this is here's the derivative of the outer at the middle, here's the derivative of the middle function at the inner, and here's the inside derivative right here, and then you clean it all up and you get whatever you get. Now, could you have done this in a problem a different way? Sure. We could have made this whole thing the cosine of 125x cubed, where only the x was getting cubed, and you get the exact same thing. It might be easier that way, but we wanted to look at it in different ways. Okay? For example 6, this says if h of x is the cosine cubed of 5x, again, think of that as the cosine of 5x, all in parentheses, with a cubed on the outside. So what's the outer function? It's something cubed. How do you take the derivative of something cubed? Well, you bring the 3 in front and leave everything else the exact same. If I were to take the derivative of 3 times x, x cubed, it would be bring the 3 in front, and then it would be times x squared. So the derivative of all of this in parentheses with a 3 on the outside would be bring the 3 in front, leave all this the same, and bring this to a 2 out here, which we know we can put here for trig notation. So now, this is the derivative of the outer function being something cubed. The derivative of that is 3 times that something squared. Now, the middle function is the cosine of something. Okay? So the derivative of the cosine of anything is going to be the negative sine of that thing. So it's going to be the negative sine of 5x. Again, the middle function would have been the cosine of 5x. Okay? So the derivative of that is the negative cosine of 5x. And then the innermost function is 5x. And the derivative of that is 5. So h prime of x is this right here. Okay? For example 7 here, this says find the derivative of this whole thing here. You can do it this way. I don't like it. I don't want to do the quotient rule, so I would prefer to change this so it looks like the product rule. Yes, product rule is generally less trouble for you than the quotient rule, so I'm going to think of this as x, and all of this to the negative 1/3, and then do the first and the second, and do the product rule here. So let's do the product rule. First times the derivative of the second gives me x times, and now the derivative of this whole thing with the power rule, general power rule that we just learned, is going to be the negative 1/3 comes in front. Okay, leave all the inside part the same and subtract 1 from the exponent. Okay, so negative 1/3 minus 1 gives us this, but now times the inside derivative, and the inside derivative of that is 2x. So then that's the first. This is the whole thing here is the derivative of the second plus, and now we need second times the derivative of the first, so that's much easier because this whole thing is the second, and there's the derivative of the first. So now let's clean it up. We need the same exact thing we had before with the least power. So notice there's an x squared plus 9 in both of these terms. We need to factor out the least power. It looks like it's going to be ugly, but it cleans up pretty nicely. So now, the least power obviously is the negative 4/3, so we're going to factor out the negative 4/3. And now, just like we did before, ask ourselves, this whole thing here times what will give me this whole thing here? So let's do it one step at a time. We're going to need a negative 1/3. We're going to need the 2x times x here, and we don't need anything out of this look here because we have the same power here. So all we need is the negative 1/3 and the times 2x squared to give us this look here. Now this part is the trickiest, but it really cleans up pretty nice because if I do this whole thing times what gives me this whole thing, remember we add exponents. They have the same base here and here, so this will have the same base. And so now I have to ask myself, this whole thing times this to the what equals this. In other words, negative 4/3 plus what exponent goes here gives me negative 1/3, and the answer is just to the first power. We don't even need to write that to the first. So when you clean it up, you get this part here is this thing here. You can combine like terms on the inside here with the x squared to get this ugly guy right here. And now you can clean it up several different ways. The way I did it here is I said that I'm going to make this x squared plus 27 over 3. Okay, so it ends up being x squared over 3 plus 27 over 3. So I get an x squared plus 27 on top, and I'm going to bring this 3 down here on the bottom. The reason I'm doing that is I want to avoid complex fractions. I can't just put this whole thing in the top and put this whole thing in the bottom, because then I'll have a 1/3 x up here, and I can't have a fraction in a fraction. So I'm going to change this whole thing so it looks like x squared plus 27 all over 3, and the 3 comes down here, and the x squared plus 27 goes up there, and that's it. You have 3 guided practice problems to try on your own. F prime is, find f prime if f of x is this. Go ahead and hit pause and do it on your own. And when you come back, here it is. There's the answer right there. Let's try guided practice 2. If y prime equals this whole thing here, think of this as the tangent of x squared plus 7x, okay, raised to the 4th power, okay, and then when you take the derivative of this, all of this is in parentheses, raised to the 4th power, so you're going to take the derivative of the outer function first, bring the 4 in front, okay, and then you're going to bring the 4 in front, so it has 4 times the tangent of all of that to the 3rd power. That's the outside function times all of this raised to the 3rd power, but we know we can put the cube right here. So again, all of this really looks like something to the 4th. What's the derivative of that? Bring the 4 in front, leave the inside part the same, raised to the 3rd. Now we need the derivative of the inside function. So what's the derivative of the tangent of anything? It's the secant squared of that thing. So we're going to do the secant squared of that thing. And now we need times the inner derivative, which is 2x plus 7. So we multiply by 2x plus 7, and we get whatever we get. It's ugly, but that's what it is. Okay. Here, what are we going to treat this like? Well, probably like we did up here with the power product rule. I'm going to think of this instead as 6x times all of this to the what? You guys go ahead and do it on your own. You can hit pause. If you did it on your own, you should have thought of this as 6x times all of this raised to the negative 1/4. Do it the same way we did up here with the least power,
and your answer is going to end up being anything equivalent to this guy
right here.
All right, guys, let me take you to these last 2 examples real quick here. So in section 2.3, we looked at derivative of cosecant. So remember, for something like cosecant, all we looked at so far was just the cosecant of x, right? There was nothing else here yet. But if there's anything else, like an exponent, or maybe that's 2x or 3x or something else, then you always have to consider the chain rule. So like I said, this is going to be embedded in everything we do moving forward. So when we say what's the derivative of the cosecant of anything, well, we say it's the negative cosecant cotangent of that thing. So again, we're leaving that interior function alone for the first step, and then we have to multiply it by the derivative of the interior function. So the derivative of x to the 3rd is 3x squared, and this is the piece that you can't forget to leave it to put in there. This is such a commonly missed thing when we do chain rules. You can't forget to multiply by the derivative of the interior function. All right, one more. And this is just going to be a product rule. Again, this is a great place to pause and give this one a shot before me if you want. But we're going to do the first times the derivative of the second plus second times derivative of the first. So we're going to start with the first, which is e to the negative 3x, times the derivative of the second. So, and this is where the chain rule comes in. The derivative of the sine of anything is the cosine of that thing. So again, we leave the interior alone, and then we multiply by the derivative of the interior function, plus the second times the derivative of the first. And the derivative of e to anything is just that item, right? E to the x is derivative of e to the x. So derivative of e to the negative 3x is e to the negative 3x times the derivative of the interior function. And the derivative of negative 3x is negative 3. And so this is what we get. From here on out, after this, it's just kind of clean up and simplify whatever you can. So you can take a look at mine, and this is what I simplified it to be after I factored out a common factor. And that's it for the first part. So, yeah, but again, be patient with this. The chain rule does take time, but we'll get good practice on this, especially for those of you guys going into calculus next year. This is something you'll for sure want to practice.